Hello! In this video, I'm going to explain how implicit differentiation works. Implicit differentiation is something that calculus students typically encounter after they've learned all the basic rules for finding derivatives, the product rule and the quotient rule and the chain rule and all that. And implicit differentiation, it sounds like it's a different kind of differentiation. But really, it's just taking those same rules for finding derivatives and using them in maybe a slightly different context. So let me start with an example that's not implicit differentiation. Let's say you're asked to find what is the slope of the tangent line to the graph of the equation y equals x squared minus 4x plus 10 at the point 3, 7. Now, when you learn about derivatives in calculus, you learn that one of the things that derivatives give you geometrically is the slope of the tangent line. If you have a function, you find the derivative of that function, and it gives you a formula for the slope of the line that is tangent to the graph of that function. So here, what we have to do is find the derivative, y prime or dy dx, and then evaluate it at the point where x is 3. And that's easy enough to do. The derivative of x squared minus 4x plus 10 would be 2x minus 4. And then when we plug in 3 for x, we get 2 times 3 minus 4, which is 2. So that tangent line has a slope of 2. Now, what about this question? What is the slope of the tangent line to the graph of x squared plus y squared equals 25 at the point 3, negative 4? At first, this looks like the same kind of question, but one thing that's different here is that we have an equation that is not solved for y. Here, we're dealing with the graph of an equation that's not set up as y equal to some function of x. Instead, the x's and y's are all mixed up together. But we still want to find the slope of the tangent line, which means we still want to find dy dx, the derivative of y with respect to x, at that particular point. So one thing we could do is we could take this equation and solve it for y, get it into that form. So we can start by subtracting the x squared on both sides. Y squared equals 25 minus x squared. And then if y squared is 25 minus x squared, that means y would be the positive or negative square root of 25 minus x squared. If we took the positive square root, we would get the top half of the circle. And if we took the negative square root, we would get the bottom half of the circle, where the y coordinates are negative. And that's actually what we want if we're interested in the specific point 3, negative 4. So because we want to know what's happening at that point, we'll work with y equal to the negative square root of 25 minus x squared. So that's what we have to differentiate. And before I actually take the derivative, I'm going to rewrite that in the form negative 1 times 25 minus x squared to the 1/2 power. Because, of course, taking something to the 1/2 power is the same as taking the square root of that thing. So for the derivative, we get, now remember, the derivative of something to a power is the power times the something to the power minus 1 times the derivative of the something. So here we end up with negative 1 times 1/2 times 25 minus x squared to the 1/2 minus 1, which is negative 1/2, times the derivative of 25 minus x squared, which is negative 2x. And we can simplify that because the negative 1/2 times the negative 2x would just be a positive 1x. And then when you have something to the negative 1/2 power, that's like taking the square root of that and putting it in the denominator. So we can write this as dy dx equals x over the square root of 25 minus x squared. Now we want to evaluate that at that particular point where x is 3. So if I plug in 3 for x, we got 3 over the square root of 25 minus 3 squared, which is 3 over 4, 3/4. So this tangent line has slope 3/4. Now, that wasn't too bad, but it did get a little messy. But we can use implicit differentiation to do this an easier way. So here's how that works. Instead of rearranging the equation, let's just leave it the way it is. X squared plus y squared equals 25. And differentiate both sides with respect to x. After all, if x squared plus y squared and 25 are equal to each other, their derivatives ought to be equal to each other. So taking derivatives of both sides with respect to x and following all the rules of derivatives, like for example, there's a rule that says the derivative of the sum is the sum of the derivatives. So when we take the derivative of x squared plus y squared, that's equal to the derivative of x squared plus the derivative of y squared. Notice I've got a d dx in front of an expression to mean the derivative with respect to x of that expression. So the derivative with respect to x of x squared would be 2x, 2 times x to the first power. And the derivative with respect to x of y squared, now if you're thinking it would just be 2y, that's not quite right, because we're differentiating not with respect to y, but with respect to x. We're thinking of y as depending on x, being a function of x. And so we have to use the chain rule. So the derivative of x to a power is just the power times x to the power minus 1, but the derivative of something other than just x to a power is the power times the something to the power minus 1 times the derivative of the something. So here we get 2 times y to the first power times the derivative of y. And I've written it as the derivative of y with respect to x. That's what dy dx means. Meanwhile, on the other side, we took the derivative of 25, and of course the derivative of a constant is 0. So now we have 2x plus 2y dy dx equals 0. I can subtract 2x on both sides, divide both sides by 2y, and then simplify that fraction by dividing out that common factor of 2, and so I get that dy dx equals negative x over y. So for any point on this circle, any point on the graph of the equation x squared plus y squared equals 25, the slope of the tangent line is going to be negative x over y. In particular, at the point where x is 3 and y is negative 4, it's going to be negative 3 over negative 4. Negative negative is positive, so that is positive 3/4. So what we mean by implicit differentiation, well, first of all, if you've got your equation set up in the form y equals some function of x, it's giving you y explicitly as a function of x. Y is explicitly defined to be whatever that formula is in terms of x. Like y equals x squared minus 4x plus 10, or y equals negative the square root of 25 minus x squared. But if the equation is not solved for y, if it's got the x's and y's all sort of mixed up together, you can still think of it as, okay, y depends on x. So that whatever number you put in for x, that kind of determines what y has to be to go along with it. So you can think of an equation like that as implicitly defining y as a function of x, possibly more than one function, like the positive or negative square root. So it's not really the differentiation that's implicit, it's the way y is defined as a function of x that's implicit. But implicit differentiation, here's how that works. So let's say you've got an equation not solved for y, but with the x's and y's all sort of mixed up together, and you either can't or don't want to solve it for y. So instead of solving it for y, the way implicit differentiation works is you differentiate both sides with respect to x, and when you do that, you're following all the rules of derivatives, And anytime any of those rules ask you for the derivative of y, write it as dy dx, the derivative of y with respect to x. Now, I've seen some books that write it as y prime, and you can do that if you want. You can write it as y prime instead of as dy dx, but I wouldn't recommend that for two reasons. I prefer dy dx. One reason is that it makes it clear that you are in fact differentiating with respect to the variable x, and you're thinking of y as a function of x. And the other reason is if you use y prime, it can be easy to get confused between the y and the y prime and to maybe lose track of one of those prime symbols and get confused about what's a y and what's a y prime. So once you've done that, then you can just solve the resulting equation for dy dx by getting all the dy dx terms on one side, all the non-dy dx terms on the other side, factoring out the dy dx, and then dividing through. Sometimes you'll be asked to find dy dx in general, just an expression for what dy dx is in general, and sometimes you'll be asked for it at some specific point, like in that last example. If you just need dy dx at one specific point, you can solve for dy dx either before or after plugging in those specific numbers for x and y. Okay, let's go on and look at another example or two. Find dy dx from the equation 2x squared minus 2xy plus y squared equals 5. And the graph of that equation is this ellipse that you see here. So to start with, we differentiate both sides with respect to x. The derivative of 2x squared would be 4x. And we need to subtract the derivative of 2xy, and we're going to need the product rule for that. It is a product. You can think of it as two things multiplied together, a 2x and a y. And the product rule says that the derivative should be the 2x times the derivative of y plus the derivative of the 2x times the y itself. And because we had a minus in front of 2xy, there's a minus in front of that whole thing that's its derivative. So don't make the common mistake of forgetting that the minus applies to that whole thing that you get from the product rule. Then over here, the derivative of y squared, again, the derivative of something to a power, is the power times the something to the power minus 1 times the derivative of the something. So now I am going to distribute that minus sign, and I don't have to do this right now, but it'll make things a little easier. I notice that every term has a factor of 2, so I'm just going to go ahead and divide both sides of the equation by 2. Simplify things a little. So now I get 2x minus x dy dx minus y plus y dy dx equals 0. Okay, I'm done differentiating. Now I want to get the dy dx terms on one side of the equal sign and the non-dy dx terms on the other side. Doesn't really matter which side is which. Here I've chosen to leave the 2x minus y on the left side and then add a plus x dy dx and subtract y dy dx on the other side. Then I can factor out that dy dx that they have in common so that it's dy dx times x minus y. And when I have dy dx times something and I want just dy dx, I can divide by the something on both sides. And I get that dy dx equals 2x minus y over x minus y. So that is dy dx. That is a formula for the slope of the tangent line, the line that is tangent to that ellipse at any given point on the ellipse. Now I do have a couple more examples to show you. So if you've got the hang of this now, you don't have to look at those other examples, but if you want to see a couple more examples, I'm going to follow this video up with another one just to reinforce what we've already been talking about.